Imagine you have just spent the last, I don't know, 3 months writing the most brilliant Python code of your entire life. You've trained a machine learning model. It is sitting right there in your Jupyter notebook, and the validation accuracy is just off the charts. You are feeling like an absolute genius.
Oh, yeah, that is the honeymoon phase of data science.
Yeah.
We have all been there.
Right. We've all been there.
Okay.
But then you hit a brick wall. Actually, you hit three massive industry-level engineering brick walls that prevent your brilliant code from ever becoming a real-world AI application. First, you have the product problem. That trained model sitting in your local notebook, it is absolutely useless to end users. You cannot hand a Jupyter notebook to a consumer or a CEO and expect them to know what to do with a Python cell. It's a science experiment, not a product.
Exactly. It's just a file on your hard drive at that point.
Yes, exactly. Second, you face the scaling problem. Let's say you miraculously wrap it in a basic web app. What happens when 1,000 users or 10,000 users all try to talk to your AI at the exact same millisecond? Your laptop or even a basic cloud server would physically melt. The system will crash or slow down to an absolute halt. And third, you run into the reality problem. Let's say you fix the scaling and get it deployed. A few months go by and suddenly your AI model starts breaking or giving completely irrational answers. Why? Not because a single line of your code changed. That's simply because the real world and user behavior changed over time. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
Going from a basic understanding of Python scripts to actually functioning as a production AI engineer requires a complete shift in how you view the lifecycle of software. The barrier to entry in this field isn't just the math or the gradient descent algorithms anymore.
No, it's the infrastructure, isn't it?
100%. The barrier to entry is the infrastructure vocabulary. The industry is just flooded with an alphabet soup of machine learning terms. You hear things like Docker, Kubernetes, RG, feature stores, MLOps. If you don't know how these pieces interact, you can't build a system that survives contact with the real world.
It's intimidating, to say the least.
It is, but here's the secret. Every single one of those intimidating terms actually fits into a logical map. Our mission for this deep dive is to decode that real-world AI engineering vocabulary and give you a master framework.
I love that. We are going to build a mental model together to trace the exact journey your code takes to go from that isolated notebook to a living, breathing, enterprise-scale AI. This journey requires moving through 5 distinct stages: store, build, deploy, enhance, and maintain. Every buzzword you hear in a daily stand-up meeting belongs to one of those 5 stages. Let's start at the very beginning of that journey with part 1, store. This addresses the fundamental question of where everything lives. Before you can do any AI engineering, before you can train a model, your data needs a home. But in the enterprise world, these homes are highly specialized, right?
They have to be. You can't just leave petabytes of data on a shared drive. The first concept you'll encounter is the data lake. The common analogy here is a giant cavernous warehouse where you just dump everything in its original raw form.
So no organization.
Very little. We are talking about unstructured data, server logs, raw text files, audio clips, massive folders of uncompressed images. You are just tossing boxes into this massive warehouse.
But wait, here's my pushback on that. If a company dumps petabytes of video logs and JSON files in there for 5 years without organizing it, aren't they just creating a data swamp? At what point do cloud storage costs actually outweigh the benefit of keeping raw, unindexed junk?
That is the exact tension data engineering teams fight every single day. It's a great point. The philosophy behind a data lake, historically anyway, has been store now, process later. In environments like AWS S3 or Google Cloud Storage, object storage is incredibly cheap compared to the compute power needed to analyze it. You dump all that unstructured data into the data lake exactly as it is because you don't know what questions your machine learning models might need to answer 5 years from now.
So it's a future-proofing strategy.
Exactly. But your point about the data swamp is a very real failure mode. I have personally seen companies accumulate petabytes of raw application logs that are so poorly tagged with metadata that finding a specific user session is literally like finding a needle in a haystack. To prevent a data lake from becoming a swamp, you need strict data governance. You need partitioning strategies, saving files by year, month, and day. You need to use efficient file formats. You don't just dump raw CSVs, you convert them to columnar formats like Parquet so that when you eventually actually do want to scan them, you aren't reading the entire massive file just to extract one single column of data.
Okay, so the data lake is the raw storage, but it requires discipline. It's like having a giant basement for your receipts, but at least putting them in folders by year. Eventually, though, you need to actually analyze that data. If the data lake is the giant, messy warehouse, we contrast that with a data warehouse, which is more like a highly organized library featuring clearly labeled shelves.
Yes, the data warehouse is where structure and schema come into play. Data engineers build what we call ETL pipelines, extract, transform, load. They take specific valuable data from that messy data lake, run it through cleaning pipelines to remove duplicates, handle missing values, standardize date formats, and then load it into the data warehouse.
So this is where the data becomes actually usable for the business.
Precisely. This is structured data. It lives in neat relational tables. It is heavily optimized for fast querying. A data lake operates on schema on read, meaning you apply structure only when you pull the data out. A data warehouse operates on schema on write, meaning the data must perfectly match a predefined structure before it is even allowed inside the doors.
That makes sense.
If a data scientist needs to quickly calculate the average user session length from last quarter to establish a baseline for a new ML model, they do not want to go digging through the raw JSON logs in the data lake. They want to run a fast, efficient SQL query in a data warehouse like Snowflake or Google BigQuery.
So we have the lake for the raw, unstructured data, and the warehouse for the clean, structured data. But there is a third storage concept that is uniquely crucial for machine learning, and that is the feature store. The analogy I usually lean on here is a commercial kitchen. If a chef gets an order for a stir fry, they do not stop everything. Walk to the fridge, wash the carrots, peel them, and chop them from scratch. That takes way too long.
Right. The customer would leave before the food arrives.
Exactly. Instead, during prep time, the kitchen staff chops all the vegetables and stores them in easy-to-reach containers. When the order comes in, the chef just grabs the pre-chopped carrots and throws them in the pan. A feature store is the centralized storage of reusable, pre-calculated machine learning features. But beyond the analogy, what does this actually look like in an enterprise architecture?
Well, in machine learning, a feature is simply a measurable property. If you are predicting credit card fraud, a critical feature might be the number of transactions this specific user has made in the last 10 minutes. You cannot calculate that massive aggregation from scratch across millions of database rows in the 50 milliseconds it takes to approve or deny a credit card swipe.
Because the latency would be unacceptable.
Exactly. So engineers pre-calculate it and put it in a feature store. But in practice, a feature store like Feast or Hopsworks does two distinct things, and this is where the engineering gets pretty complex. It manages an offline store and an online store.
Okay, break that down for me.
The offline store is backed by your data warehouse. It holds massive amounts of historical feature data used for training models in large, slow batches. The online store is backed by a high-speed, in-memory database like Redis. It holds only the latest, most current feature values for real-time inference. The actual hard part of building a feature store is keeping those two environments perfectly synchronized so that the Python code used to train the model uses the exact same logic as the real-time production system.
Ah, I see. That prevents the classic training-serving skew. If the data science team defines an active user differently than the software engineering team deploying the model will fail in production. The feature store forces everyone to use the exact same chopped vegetables. But let's talk about the nightmare scenario for a second feature leakage. If we are storing all these historical features, how do we make sure the model isn't accidentally looking into the future during training?
Oh, feature leakage is a massive issue. It ruins so many models. Imagine you are training a model to predict if a user will cancel their subscription on Friday. If your training dataset accidentally includes a feature called cancellation confirmation email sent that was generated on Saturday, your model will look like an absolute genius in training. It'll achieve 100% accuracy.
Because it essentially has the answer key.
Right. But in the real world, on Thursday, it will fail completely because that feature doesn't exist yet. Advanced feature stores solve this with time travel queries, or what we call point-in-time correctness. When you ask the feature store for a training dataset, you give it a timestamp, and it guarantees that it will only return the feature values exactly as they existed at that specific millisecond in the past, completely hiding any future data.
That is incredibly clever. Okay, that covers the store stage. We have our raw lake, our structured warehouse, and our real-time feature store. Now that our data has a home, we move to part 2, build. This is about transitioning from data preparation to creating the actual AI brain and packaging it to survive outside your local environment. This is where we need to distinguish between weights and checkpoints, or, as I like to say, the brain versus the save file. Weights represent the actual structure of the model. But what does that mean under the hood? What physically is a weight?
If you strip away the mystique of AI, a neural network is essentially a massive collection of mathematical matrices. The weights are the individual numbers, the floating point values inside those matrices. When a model is training, it is looking at data, making a guess, calculating its error, and then using an algorithm called backpropagation to slightly adjust all of those millions or billions of numbers up or down.
Just constantly tweaking the dials.
Exactly. The culmination of all those specific numbers is the learned intelligence. A modern model like Llama 3 has 70 billion of these individual weights.
So the weights are the 70 billion little dials tuned to the exact right frequencies. But what is a checkpoint? A checkpoint is simply a snapshot of those weights saved to a disk at a specific moment in time. The analogy is saving your progress in a video game right before a big boss fight.
That's a great way to picture it. When you are training a large model, it can take weeks and cost millions of dollars in GPU compute. You cannot afford to lose that progress if a server rack loses power. So engineers write code to serialize the model, saving the exact state of all those matrices at regular intervals, usually after every epoch or full pass over the training data. Those are your checkpoints.
So you always have a fallback.
Right. In industry, if someone says, let's roll back to the Epoch 5 checkpoint, they mean the model started overfitting to the data at Epoch 6, so they are loading the save file from the earlier, better state. But I should mention, the format of these checkpoints is currently a major topic in the industry. Historically, people saved Python models using a format called Pickle.
I've used Pickle. It's built into Python.
It is, but the problem is that Pickle files can execute arbitrary code when you load them. If you downloaded a malicious model checkpoint from the internet and loaded it into your environment, it could inject ransomware into your system. That is why the industry is rapidly moving towards safer formats like Hugging Face's safe tensors, which strictly store the mathematical matrices and physically cannot execute code.
Wow, that is a terrifying security flaw to have sitting in basic machine learning pipelines. So we have our perfect brain, safely saved as a safe tensors checkpoint. But how do we move it? If you send a Python script to a coworker, they inevitably get error messages because they have the wrong version of Python or they're missing libraries. That brings us to containerization, almost universally known by the tool name Docker. The simple analogy is a sealed lunchbox. You pack your meal, seal it, and it tastes the same whether you open it at your desk or on a mountain. Docker packages the model, the exact Python version, and the specific libraries into one isolated environment. But Docker is great in theory. Let's talk about the friction. When you're packing a multi-gigabyte LLM weight file into a container, your image sizes must just absolutely explode.
They absolutely do, and this is a massive operational headache for infrastructure teams. Traditional software engineers are used to Docker images being maybe 200 megabytes for a web service. In machine learning, especially with generative AI, you are copying a 15 gigabyte model checkpoint file into the Docker image. Plus, you need the massive NVIDIA CD libraries to allow the container to even talk to the GPUs.
So you're dealing with massive files.
We routinely see AI engineering teams struggling with 20 gigabyte Docker images. And why does that matter? Because when you need to quickly scale up your application to handle a surge in traffic, the cloud server has to physically download that 20 gigabyte file over the network before it can even start the application. That can take several minutes, completely breaking the speed of autoscaling.
Which brings us back to the scaling problem we mentioned in the hook.
Exactly. Engineers have to get incredibly clever with Docker layer caching, multi-stage builds, and storing the model weights on a separate mounted network drive rather than baking them directly into the container image itself.
That is a brilliant distinction. The container holds the code and the environment, but it dynamically loads the massive brain from outside to keep the lunchbox lightweight. So we have our optimized Docker container. How do we get it out the door efficiently? We use CI/CD continuous integration and continuous deployment. The analogy here is a fully automated factory assembly line that tests and ships products without human intervention. CI is the automated testing of new code, and CD is the automated pushing of that code to production. But applying this to ML models isn't as straightforward as standard web development, is it? In traditional software, a unit test checks if 2 plus 2 equals 4. It's deterministic. Machine learning is probabilistic. How do you build an automated testing assembly line for an AI that generates slightly different text every single time?
That is the core challenge of ML engineering right there. You cannot just run a standard unit test on an LLM. Continuous integration for ML requires a totally different paradigm, continuous evaluation. When a data scientist pushes a new model, the CI pipeline doesn't just check if the code compiles. It spins up a temporary test environment, loads a golden dataset of hundreds of complex test questions, and runs the new model against all of them.
And how do you grade that?
Well, often it might use a secondary, larger AI model like GPT-4 acting as an automated judge to grade the new model's responses based on accuracy, tone, and safety constraints. If the new model's aggregate score drops below a certain threshold, the CI pipeline fails the build and prevents it from moving forward.
Having an AI act as the quality control inspector for another AI is fascinating. And if it passes that AI judge, it moves to the continuous deployment phase.
Yes, but again, we don't just blindly push it to 100% of users. Advanced CD pipelines for ML use shadow deployments or canary releases. In a shadow deployment, the new model is deployed alongside the old model. The system routes real user traffic to both, but only returns the old model's answer to the user. The new model's answers are just recorded silently in a database.
So you get real-world testing without the real-world risk.
Exactly. Engineers can then compare how the new model performs on live, real-world traffic without risking a bad user experience. Only when they are confident in the shadow metrics do they flip the switch to make it live.
Let's do a quick recap. We stored our data in lakes, warehouses, and feature stores. We built our model, saved its checkpoint, packed it into a lightweight Docker container, and used CI/CD with shadow deployments to test it. The model is now ready to face the world. This brings us to part 3, deploy. This is all about connecting the model to the public and ensuring the infrastructure can survive the traffic. The first piece of that architecture is the API, or Application Programming Interface. The analogy is the waiter. The user is at the table, the model is the kitchen. The waiter takes the order from the front-end app, hands it to the back-end Python model, and brings the response back. But with modern generative AI, the waiter operates a little differently, doesn't it? When I use an AI chat app, I don't wait 10 seconds and then get a massive block of text all at once. The text streams onto the screen word by word. How does the API handle that?
Standard REST APIs are designed for request and response. You ask for a web page, you wait, you get the whole web page. But generating a long paragraph of text from an LLM takes time. If the API waited for the entire generation to finish, the user would stare at a loading spinner for 15 seconds and assume the app was broken.
Rather, just close the tab.
Exactly. To fix this, AI engineers use different protocols, typically server-side events or WebSockets. These allow the API to establish a persistent, open connection between the user's browser and the server. As soon as the inference server generates the very first token, the first piece of a word, the API immediately streams it down the open connection to the user's screen. The user starts reading instantly while the backend is still actively computing the rest of the sentence. It drastically improves the perceived performance of the system.
So the API is managing that streaming connection.
Right.
But it's handing the request to the backend.
Yep.
And on the backend, we don't just use a basic web server, we use an inference server. Right. Why can't I just wrap my model in a basic Python Flask app and call it a day?
If you are building a hobby project for 5 users, a basic Flask app is fine. But generating a prediction from a deep neural network, which is the active inference, requires highly specialized management of the GPU hardware. Let's look at the mechanics. If 2 users send a request to a basic Flask app at the same time, the app processes one, then processes the other. That leaves the massive parallel computing power of the GPU sitting idle.
So it's incredibly inefficient.
Incredibly. An optimized inference server like VLLM or NVIDIA Triton uses algorithms like continuous batching. It intercepts incoming requests from dozens of users, bundles them together into a single mathematical matrix, and pushes that entire batch through the GPU simultaneously. Furthermore, it manages something called the KV cache, the temporary memory the model uses to remember the context of the conversation. GPU memory bandwidth is actually the biggest bottleneck in AI today, not compute speed. An inference server is specifically engineered to squeeze every millisecond of performance out of that expensive GPU memory.
The inference server is the highly tuned engine. But if your app goes viral, you have a stadium full of people submitting requests. One inference server will get overwhelmed. How do we survive this? We call in Kubernetes, often abbreviated as K8s. The analogy is the air traffic controller. If Docker is the lunchbox, Kubernetes manages thousands of those lunchboxes. If it sees your server getting overwhelmed, it spins up identical copies of that container across different machines. But I have to ask, Kubernetes is notoriously complex. I hear engineers complaining about it constantly. Is it always necessary?
It is incredibly complex, and frankly, many small startups adopt Kubernetes prematurely and drown in the operational overhead. But at enterprise scale, it is non-negotiable. Here's why it is so painful but necessary for AI. AI workloads are stateful and hardware dependent. Kubernetes has to monitor the traffic hitting your API. If the traffic spikes, the horizontal pod autoscaler realizes it needs more capacity.
But it can't just throw the container anywhere.
Right, it can't just spin up a container on any random server. It specifically has to request a cloud instance that has NVIDIA GPUs physically attached to it. It has to wait for the cloud provider to provision that expensive hardware, pull the giant Docker image, and mount the model weights. The orchestration required to manage GPU nodes, ensure the models load correctly, route traffic only to the containers that have fully booted, and then scale them back down to save money when traffic drops is a monumental engineering feat. Kubernetes handles that orchestration, but configuring those scaling thresholds takes deep expertise.
Which brings us perfectly to the user experience side of that scaling process. This involves two concepts that go hand in hand: latency and cold start. Latency is simply response speed. Lower is better. But latency is heavily impacted by the cold start. The analogy is trying to start your car engine on a freezing winter morning. If a Kubernetes node hasn't been used in a while, it spins down to save money. When a new user makes a request, the system has to provision the GPU, pull a container, and load the multi-gigabyte weights into the VRAM. I remember talking to an engineer at a fintech startup who thought they had a massive memory leak because their system was crashing every night at 2 a.m. Turns out, it wasn't a leak. It was a cold start issue. A scheduled automated job hit the API with thousands of requests all at once. Because the system had scaled down to zero overnight, the sudden spike caused Kubernetes to panic, try to spin up 50 massive GPU nodes simultaneously, and essentially DDoS their own internal network because the cold start took too long.
That is a classic cloud engineering horror story. A cold start for a large AI model isn't just a 2-second delay. It can take 30 to 60 seconds to move 70 gigabytes of weights from storage into the GPU memory. A user will not wait 60 seconds for a chatbot to reply. To solve this, engineering teams often use provisioned concurrency. They pay the cloud provider a premium to keep a minimum number of GPU instances permanently running and warm, even if no one is using them. It is a direct trade-off between user experience and massive infrastructure costs. Alternatively, they use smaller, heavily quantized models for initial fast responses while the larger model warms up in the background.
We have one more crucial concept in the deploy stage. This is a massive point of confusion: token limit versus rate limit. These sound similar, but mixing them up causes major headaches. Let's delineate. The token limit is the brain capacity of the AI. It is the maximum context size the model can process before it literally forgets earlier text. A rate limit is the traffic light. It is how many requests you are legally allowed to ask the API provider per minute. But let's dig into the token limit first. Why does the model forget? Why can't I just paste a 1 million word book into a standard model?
To understand the token limit, you have to understand how models actually read. Models do not read English words, they read tokens. They use an algorithm like byte pair encoding to chop words into subword chunks. The word hamburger might be 3 tokens. The limitation comes from the core architecture of modern LLMs, the attention mechanism. When a model processes text, every single token has to mathematically pay attention to every other token to understand the context. If you double the length of the input text, the computational memory required doesn't just double, it squares. It scales quadratically.
Wow, so the memory cost skyrockets.
It does. If you try to feed a massive book into a model not designed for it, the GPU simply runs out of VRAM and crashes. The token limit is a hard mathematical hardware constraint.
Contrast that with the rate limit, the traffic light. This has nothing to do with the model's memory. This is an API usage restriction set by your provider, like OpenAI or your own internal API gateway.
Exactly. If you have an internal app, your API gateway will implement rate limiting, often using a token buck algorithm to prevent any single user from hogging all the GPU compute. It might say a user can only make 50 requests per minute. If you send 51, the API gateway intercepts it before it even reaches the inference server and returns an HTTP 429 error, which means too many requests. So to summarize for our listeners, token limit equals memory capacity of the brain, rate limit equals usage control of the infrastructure.
Token is brain, rate is traffic light. Excellent. Let's review the map. We stored the data, built the package, deployed it to the world, and managed the traffic. But sometimes a standalone language model isn't enough. It doesn't know private company data, and it can't take actions. How do engineers give it superpowers? That is part 4. Enhance. The foundational tool for this new era of dynamic AI is the vector database. The analogy is searching the internet by the vibe or meaning of what you want, rather than relying on exact keyword matches. Traditional databases require exact keyword matches. If I search a SQL database for happy dog, it misses a document that says joyful puppy. A vector database solves this. But how does a vibe translate into math?
This is where we get into the mechanics of embeddings. Before text goes into a vector database, it is passed through a specialized AI called an embedding model. This model translates a sentence into a dense vector, a massive array of floating point numbers, often 1,536 dimensions long. You can think of this array as a specific set of coordinates in a high-dimensional mathematical space.
So it's plotting words on a massive graph.
Yes. The embedding model is trained to place conceptually similar ideas physically closer together in this space. Happy and joyful will have coordinates that are very close to each other. When a user queries the database, their query is also converted into a vector. The database doesn't look for matching letters. It uses algorithms like HNSW hierarchical navigable small world to rapidly calculate the cosine similarity between the vectors. It mathematically finds the nearest neighbors. It retrieves information based on semantic closeness.
This meaning-based search is the engine behind our next term, arguably the biggest concept in enterprise AI right now, RH, Retrieval Augmented Generation. The analogy is an open book exam. An LLM on its own hallucinates because it relies entirely on its static training memory. RH allows it to look up facts. The pipeline is search the vector database, retrieve relevant paragraphs, augment the user's prompt with those paragraphs, and force the LLM to generate an answer based only on that retrieved text. But let's push back on naive RH. Doesn't it just blindly grab the first search result and paste it in? If the retrieved document is garbage, the AI's answer will be garbage.
Absolutely. Naive RH just slapping a vector search in front of an LLM fails in production constantly. The retrieval phase is incredibly difficult to get right. If you have a 100-page PDF, you can't embed the whole thing as one vector. You have to use chunking strategies. Do you split the text every 500 words? Do you split it by paragraph? If you split it abruptly, you might cut a sentence in half, destroying the context. Engineers use overlapping chunks to preserve meaning.
Even then, semantic search isn't perfect, right?
Not at all. A query for what is the company's sick leave policy might retrieve a document about health insurance benefits because the concepts are semantically close, completely missing the actual sick leave paragraph. To fix this, advanced RH systems use a two-stage process. First, the vector database retrieves the top 20 vaguely related chunks. Then, a secondary, highly precise model called a cross-encoder reads all 20 chunks and rigorously re-ranks them based on exact relevance to the user's specific question, feeding only the top 3 to the final LLM.
It is a deep pipeline of specialized tools just to get the model to read accurately. But we can take this even further. RAG allows the AI to read. But what if we want the AI to actually do things? This brings us to agentic AI, the autonomous worker. The analogy is upgrading from a basic search engine to a proactive personal assistant who plans steps, uses tools, and executes tasks. A traditional LLM is a reactive chatbot. You prompt, it answers, it stops. Agentic AI has a reasoning engine. It breaks a massive goal down into smaller logical steps.
The agentic workflows represent a paradigm shift. Engineers use frameworks like LangChain or LangGraph to give the AI an internal scratchpad or memory. The core mechanism is often called react, prompting, reasoning, and acting. You give the agent a goal. The agent first outputs a thought. I need to find the current stock price of Apple. Then it outputs an action, it executes the action, observes the result, and then generates its next thought. Now that I have the price, I need to format it into a report. It loops through the state machine autonomously.
But letting it loop autonomously sounds dangerous.
Oh, it introduces severe failure modes. If the agent encounters an error, it can get stuck in an infinite loop, continuously trying and failing the same action, burning through expensive API credits every single second. I've seen agents burn $50 in an hour because they got stuck trying to parse a broken website. You have to engineer strict circuit breakers, maximum loop counts, and fail states to manage autonomous agents.
That is wild. It creates its own to-do list, but you need guardrails so it doesn't obsess over one task forever.
Yeah.
But how does it actually execute that to-do list? It's just software. How does it research a competitor or format a table? That is our final enhanced concept. Tool calling. Tool calling gives the AI the ability to invoke external functions.
If the agent is the brain, tool calling provides the hands. During the initial system prompt, engineers provide the LLM with a strict JSON schema, an API specification detailing the tools it has access to. For example, a calculator, a SQL query executor, or a live web search. When the agent is reasoning and realizes it needs to multiply large numbers, it generates a specific JSON payload structured exactly as the tool requires. The application code pauses the LLM, takes that JSON, runs the external Python calculator script, gets the result, and injects it back into the LLM's context.
It essentially pauses its own thinking to use a calculator.
Exactly. But giving AI tools introduces massive security risks. If you give an LLM a tool that can execute arbitrary SQL queries, a malicious user could theoretically prompt inject the bot and tell it to drop your entire user database. Engineers must sandbox these tools heavily, enforce read-only permissions, and often implement a human-in-the-loop approval step before the AI is allowed to execute any destructive action, like sending an email or deleting a file.
So it knows its limitations, calls external functions, but it's kept in a strict sandbox. We've enhanced the model. Vector databases, RAG, agents, tool calling. We have an absolute powerhouse. Are we done? No, because software decays. And ML models decay faster than normal software. This brings us to our final stage, part 5, maintain. Putting a model into production is the starting line, not the finish line. This leads to monitoring, the health check, just like going to the doctor. But we aren't just looking to see if the server crashed.
No, traditional software monitoring looks at infrastructure metrics like CPU usage, memory, and latency. Those are necessary, but entirely insufficient for AI. You can have an AI system where the CPU is perfectly fine, the latency is a blazing fast 50 milliseconds, and the HTTP status is a green 200 OK. From an IT perspective, the system is perfectly healthy, but the LLM could be rapidly generating hallucinatory, toxic garbage. In the maintain stage, engineers have to monitor statistical and operational ML metrics. They monitor token generation speed, they log a percentage of user inputs and model outputs, and use smaller, cheaper models to continuously scan those logs for sentiment drops, toxicity, or repetitive loops.
And monitoring is crucial because it allows you to catch the silent killer of machine learning models. Model drift. This concept is fascinating. Model drift is the intuitive explanation of why AI breaks in the real world. The Python code didn't break, the math didn't change. What happened is that the world changed.
Drift happens when the underlying data distribution shifts. There are two main types to worry about: data drift and concept drift. A classic example of concept drift is the global pandemic. Imagine a retail company trained a highly accurate model on 5 years of pristine data to predict inventory needs. The model learned that business suits sell well in autumn. Then 2020 happens. Overnight, human behavior shifts. Everyone stops buying suits and starts hoarding toilet paper and webcams.
The model didn't know the world changed.
Right. The model confidently predicts you need more suits because its baseline reality no longer matches the current world. It fails completely. Data drift is more subtle. Suppose you have a model diagnosing X-rays, trained on scans from a high-end machine. The hospital buys a new, cheaper X-ray machine that produces slightly grainier images. The fundamental concept of what a bone looks like hasn't changed, but the statistical properties of the incoming pixels have drifted. The model's accuracy plummets. Engineers use statistical tests like KL divergence or population stability index to continuously compare the live incoming data against the historical training data to detect this invisible decay.
The world changed, so the brain has to be updated. The umbrella term that encompasses all of this maintenance, versioning, deployment, and monitoring is our final term: MLOps. Machine learning operations. It's the overarching practice of DevOps, specifically tailored for ML.
MLOps is the glue. It's not just a specific tool, it's a cultural shift. It means treating machine learning not as a Jupyter Notebook experiment, but as highly reliable production software. It utilizes platforms like MLflow, Kubeflow, or AWS SageMaker to create a model registry. Every single time a model is trained, MLOps tracks exactly what dataset was used, what the hyperparameters were, and what the final accuracy was. If model drift occurs in production, the MLOps pipeline automatically triggers an alert, pulls down the fresh drifted data, kicks off a retraining job on the CI/CD pipeline, tests the new model, and seamlessly swaps it into the Kubernetes cluster. It creates a closed, automated loop of continuous improvement.
It's the professionalization of AI engineering. We have covered the entire 5-stage framework: store, build, deploy, enhance, maintain. To prove that you can now navigate this landscape, we're going to do a rapid-fire translation drill. For you listening, this is how you apply this map in the real world. I'm going to read a sentence filled with terrifying industry jargon, and our expert speaker is going to provide the plain English translation to show you how to parse this language. Ready?
I am ready. Let's map the vocabulary to the concepts.
Drill 1. The jargon. We deployed a containerized arg system with CI/CD and minimized cold start.
The translation. We packaged an AI system that retrieves documents before answering into an isolated environment, automated the testing and updates, and paid extra to keep the servers warm so users don't experience startup delays.
Beautiful. Drill 2. The jargon. We hit the rate limit.
The translation. We exceeded the allowed number of requests governed by the API gateway, returning a 429 error.
Simple as that.
And
Drill 3. The jargon. We used the V3 safe tensors checkpoint.
the translation. We loaded a specific, securely saved version of the model's learned mathematical weights to avoid executing malicious code.
Incredible. The intimidation factor vanishes once you know the architecture behind the words. Let's synthesize. Your data starts in the store stage, moving from the messy data lake to the structured warehouse to the real-time feature store. You build, taking the trained weights, saving checkpoints, packaging them in Docker, and using CI/CD to automate evaluation. You deploy, using APIs with streaming WebSockets, inference servers managing GPU memory, and Kubernetes orchestrating the traffic, while balancing cold starts against token and rate limits. You enhance the models using vector databases and embeddings, RAG for factual reading, agentic AI for autonomous reasoning, and tool calling to take action. Finally, you maintain the system, using MLOps to monitor operational health and watch out for the silent killer of model drift. Every engineering conversation fits on this map.
This mental model is the scaffolding.
Yeah.
When a new tool is released next week, you don't need to panic. You just ask yourself, does this help me store data, build models, deploy them, enhance them, or maintain them? It anchors you in reality.
Now that you have the mental map and vocabulary of how modern AI systems operate in production, our next lesson will take you hands-on. We will actually build your very first automated CI/CD pipeline for a basic machine learning model. We're moving from the map to the real terrain. But before we go, I want to leave you with a final provocative thought to ponder. If agentic AI is learning to use tools, and MLOps is the toolset for monitoring and fixing models, how far are we from agentic AI that monitors its own model drift, diagnoses its own data shifts, and automatically triggers its own CI/CD pipeline to heal and retrain itself without any human intervention? We have an exercise for you. Try translating one piece of AI jargon you've heard recently using the 5-stage framework. Write your answers and any questions you have in the comments below. And of course, if this lesson gave you that aha moment, make sure to like, share, and subscribe to 60 Seconds Academy for more industry-ready AI engineering deep dives.